So we're gonna work with some nitriles. So remember, we actually reviewed a few class periods ago how to use alkyl halides and cyanides, or how to make cyanohydrins. So this is going to be really important for this upcoming exam. And we're going to revisit some organometallic reagents. So you'll remember, based on our periodic trends, when we have magnesium or lithium bound to our carbon, we know that our carbon is nucleophilic because of those electronegativity differences. So we're going to revisit some nucleophilic reagents today that are organometallics. All right, our learning objectives that we're going to go through, a little bit of a random selection of topics today, but at the end of the day, this is the carboxylic acid derivatives chapter. So we're either going to get to a carboxylic acid derivative or we're going to use a carboxylic acid derivative, right? So Professor Lamb has talked a lot about the various reactivity spectrum of carboxylic acid derivatives, what reacts with what and what doesn't. So we're going to talk a lot about that today, and we're going to use some strong nucleophiles and organometallics. All right, let's go ahead and get into our first topic, which is going to be a dehydration reaction. So this is going to be learning objective 20J. And here it's going to be the 2Ps. So we're not going to worry about a mechanism for this reaction today. This is just predicting the products and knowing the starting materials. So it's the 2Ps of formation of nitriles. Right, so this is another way, I asked you to review how you form nitriles, but here's another way to do it. So this is going to be through dehydration. So we're going to get water out of this reaction because it's a dehydration reaction, and it's going to be dehydration of amides. So this is our carboxylic acid derivative, which is why it's included in this chapter. If you're following along in the book, this is 20.15. Right, so we decided to go a little bit out of order of some of these topics based on the book because sometimes it fits a little better to put, all the nitriles and amides and things like that together. All right, so our learning objective tells us, of course, what our starting material is, right? So we're going to start out with an amide. So I'm going to draw out that carbon because we're going to need it sort of suggestively. So here we have a primary amide. Our nitrogen isn't bound to anything. We have this NH2. All right. And then at the end of the day, our learning objective tells us that we're going to form a nitrile. So we're going to carry this R group through. We're going to have our carbon. And then we're actually going to form a nitrile. So 3 bonds between our carbon and our nitrogen. All right, when we take a look at this amide, we see that we're missing some things. So let's draw on our byproducts. We see that our oxygen comes from our amide, and then we see our NH2 turned into a nitrogen with a triple bond. So we need those hydrogens go somewhere, and so that's why we have water in this reaction. All right, so another thing I want to re-emphasize that we've talked about before a little bit is the fact that this is not an oxidation reaction, right? So even though we see, wow, carbon has 3 bonds to nitrogen, so 3 total bonds to a heteroatom meaning something other than carbon, so something like nitrogen and oxygen, we have 3 bonds to carbon. Here we also had 3 heteroatom carbon bonds, right? So this is not an oxidation reaction. This is a dehydration reaction because we've lost water. All right, so what are the conditions for this? We're going to need a little bit of heat for this, actually quite a bit of heat. We're going to heat this up to about 200 degrees Celsius, so it's pretty warm. And then we're going to use a dehydrating reagent called P4O10. All right, and so what P4O10 does is it reacts with water, all right? So basically, our heat is going to do this dehydration for us. We don't need to know the mechanism at this point. And then this is where our P4O10 comes in, all right? And it reacts with water to form phosphoric acid. Right, so we know our equilibrium can be pushed forward if we take out some of our products. And so this is an irreversible reaction because the phosphoric acid is from the water that forms. All right, So when I was a graduate student, I don't know, we always called this P2O5, and I think more studies were done on it. So sometimes you'll actually hear me mistakenly say P2O5, but it's the same as P4O10. All right, so this is what's called our dehydrating reagent. So we've dehydrated, we've lost water in this reaction. Right, we know other ways to remove water from a reaction, right? A Dean-Stark trap and things like that. Well, this is a chemical way when we react with water as opposed to using a piece of glassware. So the other thing I want to point out here that I mentioned, right, is that primary amide is necessary. So we need those two hydrogens to form our water. We can't do this with like a dimethyl or two methyl groups on our nitrogen. All right. So this is, we don't need to know the mechanism of this reaction. It's pretty straightforward as far as our reagent. We just need to heat this up with a dehydrating reagent. All right, so let's do a little bit of retrosynthesis or a practice problem to see how we can get here, right? So always the last problem on the exam is that multi-step synthesis. So it's always good to practice with some real molecules. So what if we started out with this particular carboxylic acid? What if we wanted to go to this nitrile? All right, so we just learned the step to go from an amide to a nitrile, but we also know from earlier chapters how to actually make an amide from a carboxylic acid. It's going to take a couple of steps. So I'd like you all to think on this on your own for just a moment and see what you can kind of come up with for our retrosynthesis, right? We're not adding our reagents at this point. We're just going backwards and seeing how we would make this. So I'll tell you there's probably multiple ways to make this, but you can make it using two different intermediates past this. So 3 retrosynthetic arrows to get to those. And once you have a few things jotted down, you can go ahead and check with your neighbor if you want, see what their thought process is to get to this product. I'll suggestively say that, we haven't added any carbons in this, right? We see that carbon carried throughout. Okay, so let's see what one way to make this molecule would be, all right? So we can take our amide that we just learned about, that dehydration, right? It has to be that primary amide. This is what we just learned about. So how can we actually make amides? It takes, we can't really make them directly from the carboxylic acid. We need to go through something that's a little bit more reactive. And so what if we went through, for example, an acid chloride? All right. So we remember Professor Lamb taught you the sort of scale of reactivity. Acid chlorides are very reactive and they can make amides. And so we could get there through this retrosynthetic route. All right. So for practice on your own, when you're going back through the notes, practice the reagents. So add in your reagents to go in the forward direction. And if you're having a tough time with this, remember, you can always post on the discussion board and see what the TAs and your fellow lab mates think. All right, so that's a little bit of a kind of seeing this nitrile formation in the context of a multi-step synthesis. Let's launch into our next learning objective, all right? So this is a learning objective 20K. All right, this is going to be a 4P reaction. So we are going to learn the mechanisms of both acidic and basic conditions. I'm going to go through the acidic one, and then I'm going to get you partway through our basic one, and then I'm going to have you practice that on your own. So This is the 4 Ps of nucleophilic acyl substitution. So we know the mechanism. And we're going from nitriles, right? We just learned another way to make those, to carboxylic acids. Kind of the opposite of the reaction that we had our multi-step synthesis with. If this is under basic conditions, we're going to say these are going from the carboxylates, right? So just to be precise there. And so we call this hydrolysis as a class of reactions. We're going to do this under both basic and acidic conditions. All right, so this is a pretty long learning objective. So let me see what this is 20.16 in your book. All right, so our learning objective tells us that we are going to start out with a nitrile. All right, so I'm going to draw some key parts of this here so we can kind of track along and see where this goes. All right. Our learning objective also tells us exactly what our product is. If it's under acidic conditions, it's a carboxylic acid. Under basic, we'll have to do a workup, but it'll start as a carboxylate. All right, so we can kind of see where this is going. We see our carbon stays intact, and we're going to form a carboxylic acid. All right. And I'm going to say plus byproducts. And these byproducts are going to be a little different depending on if this is acid or base as our conditions. All right. So this is the overall reaction. We're taking a nitrile, it's doing a hydrolysis, and we're ending up with a carboxylic acid. All right. So let's see where our conditions are going to be for acidic conditions. All right, we're going to use, of course, an acid here. So let's see what type of acid we can use. And we're going to use water as well. So we're going to use H2SO4 and water. All right, and so we see that our water is going to be incorporated into our carboxylic acid. And of course, we have to lose a nitrogen, right? So we have a lot of excess acid around. So what we're going to lose is an ammonium sulfate. We have our SO4 minus is going to be our counterion. All right. So because this is under acidic conditions, we're not going to lose ammonia. We're going to lose an ammonium salt, right? The IUM means it's cationic. In our conditions, that's why it's positively charged. So of course we have to have our counterion. All right, let's see what the basic conditions look like. It's going to have different byproducts, right? Because now we don't have that extra acid to form our ammonium salt. So we're going to start out with that same nitrile. We're still going to end up with a product that incorporates our 2 oxygens, but because we're under basic conditions, we know that we're going to get a carboxylate out. So a negatively charged species. Because we know the pKa of a carboxylic acid is it's very easy to deprotonate. So in this case, we're going to use KOH. So I'm going to have this as a potassium hydroxide potassium counterion with a little bit of water. If you wanted to use sodium hydroxide, that's totally fine. You just need to have a strong base. Okay, so what is the byproduct in this reaction? I told you it's not going to be an ammonium salt. It's going to be ammonia. All right, so we're going to have some hydrogens from our water. Ammonia, it turns out, is a gas. All right, so the gas will bubble off in your reactions. Right, so we're always talking about equilibrium in this class, right? And if we can have our byproduct go away, then the equilibrium can be driven forward in this reaction through loss of a gas, right? So we don't want the carboxylate out at the end. We know we always do a acidic workup in this class. So H3O plus workup in a separate step, right? If we added H3O plus in our original reaction, it would no longer be under basic conditions. You just have H3O plus react with KOH. And this will end up giving us our carboxylic acid, which is our desired product at the end of the day. Right, so at this point in the class, I would encourage everyone to sort of make sure the acidic and basic conditions make sense to you with the types of products that we form, all right? This is going to be really helpful for mechanisms, right? We know in mechanisms we need to make sure under acidic conditions we're not eliminating out hydroxide, and under basic conditions, you know, we don't have a whole lot of protonated species, right? So please make sure that this makes sense to you, why we use different conditions and get slightly different products. All has to do with the fact that this is a pretty acidic proton, all right? All right, let's look at the P4, the mechanism for this reaction, all right? We're gonna have a lot of proton transfers here. This is probably one of the longest, if not the longest mechanisms that we've seen before, but as always, I try to encourage you to not just memorize this. This is gonna be probably too many arrows to memorize, but let's really try to understand what could be going on in this reaction, all right? All right, so let's start out with our nitrile. So I'm gonna draw in this configuration so we can kind of see some analogies to our carbonyl compounds that we've seen before. Okay, so I suggestively drew in that lone pair on our nitrile. It's not a very good base, but we have a very good acid in H2SO4, right? So we can have our H2SO4 proton get deprotonated by our base, right? Our nitrogen lone pair can deprotonate that OH bond. Right, we've seen this a lot of times before, right? We're trying to make our electrophile more electrophilic. Okay, so that puts a positive charge for us on our nitrogen because now that lone pair is no longer available, we now have it protonated. So we have a positive charge here. All right, when we're thinking about the electrophilic position here, we should always think about what our product is at the end of the day. We have some water in this reaction. Our product is the hydrolysis. We need to start to incorporate oxygen into our molecule. The other things that we know are that we talked a lot about carbonyl carbons, right? And this nitrile carbon looks pretty electrophilic because that very electronegative oxygen element, or nitrogen element number 7, is pulling electron density away from that carbon. And so that's why we know that our water can go ahead and attack that carbon. When we make an oxygen-carbon bond, we need to break a carbon-nitrogen bond, right? Because carbon can only have 4 bonds to it. All right, so we've made one of the bonds that we need in this reaction. All right, and we've broken one of our nitrogen bonds. So now it's a neutral nitrogen. And we haven't done anything with our water to deprotonate it yet. I forgot to carry through our HSO4 minus counterion in the last one, so let's go ahead and carry that through. And we'll go ahead and carry it through here. Our HSO4 minus is along for the ride here. All right, so we've made one of our desired bonds. Let's go ahead and neutralize this species so that our OH group is not positively charged. So we'll take the lone pair of electrons on oxygen of your sulfate counterion. If you wanted to use water for this, that would be completely fine. We can break that OH bond. As Professor Lamb discussed, proton transfers are very fast, and it's sometimes hard to tell what is going to be doing the deprotonation. So as long as you just had a base there, that would be fine. So now you've regenerated your H2SO4, right? So that was our acid catalyst, has now been regenerated. All right, let's check in with our product here. So we're getting closer to what we're interested in. We've broken a carbon-nitrogen bond. We need to break them all. We've incorporated one of our oxygens into this intermediate here. All right. So we've looked at this step before. It's called a tautomerization. And Professor Lamb is going to go over the very specific mechanisms for that. So we've decided to separate this out because this is such a long mechanism. And so you will learn about this, but I'm just going to show the product of tautomerization. You're not responsible for the arrows until Friday. So you will be responsible for the arrows. All right, so we're going to get to this product. What we've done in a tautomerization is we've been able to isomerize our intermediates to what is an amide. All right, so this is getting closer, actually, right? We've made an amide intermediate. It's getting much closer when we check in with our product that we need a carboxylic acid and we need nitrogen. All right, so what I'm going to do is for us to be able to see this a little bit better, I'm going to draw this in a way that you're a little bit more familiar with taking a look at, which is to have our amide here. Right? All I've done is just move this molecule about 120 degrees and flipped it over. All right, so this is going to be easier for us to see what's going on in this reaction. Okay, so we have acid here. We need another equivalent of water to be able to come in for this mechanism and ultimately displace that nitrogen. So let's go ahead and actually make our carbon a little bit more electrophilic. We're going to make it more electrophilic by having our protonation step happen. All right, so we knew we regenerated our H2SO4. We have that lone pair on our oxygen that can come in and deprotonate our OH so that now we have a more electrophilic carbon because that oxygen is now positively charged, right? So that's a product of this reaction or this mechanistic step is that we now have a positively charged oxygen, which of course we know has made our carbonyl carbon more electrophilic. Right, water isn't a great nucleophile. That's why we need to have these either acidic or basic conditions to be able to do this step. Again, I give you a moment to catch up because this is a long mechanism. But we've seen this step before, right? We've seen carboxylic acids derivatives undergo reactions, right? So this is going to look a little bit more familiar. We're going to have an addition of our water. We're going to have some proton transfers. We're going to have elimination of our amine in this reaction, all right? So this should look a little bit more familiar to things that we've seen before. All right, I'm going to carry our HSO4 counterion through as well. We're going to have water come in. And that water is going to attack our carbon and break another CO bond, all right? So now we're getting closer to the product that we're interested in. Right, because we've broken a CO bond from the CO double bond, we now have that OH on top as a neutral species. We've made a new bond between our carbon and an oxygen of water. We haven't done proton transfers yet, so it's still protonated. We have our amine in this case. Right, we've talked a little bit about resonance structures. You might say, well, why didn't our nitrogen get protonated? Well, I'm going to let you think a little bit about the resonance that we could potentially have to make this particular oxygen in this step more nucleophilic, all right? So that's just a tip for you about if you're wondering why I chose to protonate our oxygen. All right, so we'll just carry through our HSO4 counterion because we now have a charged species. Okay, so Professor Lamb had a bit of a discussion with you all about proton transfers. I'm going to do an intermolecular proton transfer here to go ahead and deprotonate this OH bond to neutralize this species. All right, so all of this is getting us to the part where we had our addition step in our mechanism that we've seen in these carboxylic acid derivatives. So now we know, based on the mechanistic patterns that we've learned about, that we need an elimination step to form our final product, right? All these are in equilibrium, so certainly you could eliminate out water and then you'd go backwards, but to go forward in the forward direction, we need to go ahead and eliminate out our nitrogen group, right? So we're under acidic conditions. We know that we're not going to want to eliminate out NH2 minus. So that means we're going to want to protonate our nitrogen. All right, this is not an amide anymore, so we don't need to worry about that resonance. So we can go ahead and say that lone pair is available to us to break that OH bond. We're going to protonate that nitrogen. We're going to get it ready to be a better leaving group. We've protonated it. We have a positive charge on nitrogen because it has 4 bonds to it. And HSO4 is going to be our counterion. All right. I told you this is probably the longest mechanism we've done in this class. We're ready to be close to be able to bring this home now. All right. So all of this mechanism here, we went through the addition step here in our proton transfers. Now we're ready for our elimination step in this type of mechanism. All right. And so we've seen before our lone pair assisted elimination reactions before, right? We've seen those lone pairs come down and cause us to eliminate out a group. So we're going to do exactly that. I've arbitrarily chosen this top oxygen. You could certainly do it with the other one. It really doesn't matter. All right, so we can have a lone pair of electrons come down, make a CO double bond, and that will cause the breaking of our carbon-nitrogen bond. And the electrons in that bond will be returned to our nitrogen as a lone pair of electrons. All right, we're very close to the end of this mechanism. Thanks for sticking with me through it. Because we took a lone pair and we made it into a bond, we now have 3 bonds to oxygen, that top oxygen, so we know that it's positively charged. What we have eliminated out at this point is NH3. Because we broke the bond, we went ahead and made it into a lone pair of electrons on nitrogen. Right? So now the strongest base in this reaction is going to be our ammonia, right? I told you proton transfers can be kind of ambiguous, and so maybe sulfuric acid is going to come around and protonate it, and then water or sulfate will deprotonate this, but we'll just use our strongest base in this reaction to go ahead and deprotonate that OH bond and neutralize it. All right, that means we've gotten to our product, which is our carboxylic acid. And we've also generated our byproduct, which was that ammonium salt. And I should have HSO4 minus here on our other structure. All right, that was a lot, right? But at the end of the day, it's an additional elimination, and we've been able to see this before, right? So please make sure you understand what types of groups can be eliminated out under acidic conditions versus basic conditions, all right? I will admit, this is the longest mechanism I think that we've done. It's many arrows, so it's going to be really hard to memorize this one. So let's try to think about some of that fundamental understanding of our electrophilic and nucleophilic positions and how we're going to get to our product here. All right. Remember, if you're getting caught up in a mechanism, you can always think about the byproducts that form, and that will help you sort of get to the end and understand. At the end of the day, for example, we had to break our carbon-nitrogen bond, even though it's a triple bond. All right, I'm going to get you started on the first step of the basic conditions of P4, and then I'm going to have you finish the mechanism on your own, all right? because once we get to the addition elimination part of the mechanism, it should be far more familiar to you. All right, so these are our basic conditions. It's a little bit more simple with basic. All right. So under basic conditions, right, even though this is a relatively weak electrophile, under acidic conditions, we protonated it to actually get it to react. Well, we have basic conditions, so we have a better nucleophile. We don't need to make this into a better electrophile because our nucleophile is just better. So we can take our potassium hydroxide. This looks like a pretty good candidate for a nucleophile in this reaction, right? We use this instead of water, right? That O minus, that OH minus is far more nucleophilic. So we'll start our arrow from a lone pair of electrons on the oxygen. It's going to attack our carbon that's triple bonded to our nitrogen, right? That's our electrophilic position because the electron density is pulled away from that nitrogen. And then when we attack that carbon, we need to break a CN bond. Right, so this is just a nucleophile attacking something. This isn't a carbonyl with an oxygen, but we have certainly seen this analogous reactivity before. All right, so our counterion here, we can just carry through is our potassium. So we know the other conditions in this reaction are going to be water. We're going to regenerate our hydroxide too, right, throughout this reaction. So we have a negatively charged nitrogen. So that means it has actually 2 lone pairs of electrons on it. All right, and we can take the electron density. We can go ahead and deprotonate water, breaking that OH bond. We haven't done anything to the carbon-nitrogen double bond. All we've done is just protonated our nitrogen. So now we've neutralized the species. All right, we're going to do this step, which you're going to learn about, the tautomerization step. You'll learn the mechanism on Friday. And we're going to get from this tautomerization, what we end up with is an amide, just like we saw in our other mechanism. Tautomerization is acid and base catalyzed. So that's one of the reasons we can do it in both cases. Right, so this is a little bit easier under basic conditions, okay? So what we've done is we've added in our hydroxide, we've done some proton transfers, and we get to our amide. All right, and at this point, you've seen amide chemistry before and how those react. So I'm going to ask you to finish on your own. All right, and if you have questions about this, you want to draw it out, you want to upload a picture to the discussion board, you can go ahead and check your answer that way. All right, so that was a really long mechanism that we had for our hydrolysis. We had to break a lot of bonds, right? We had a carbon triple bonded to our nitrogen. So we had to break a lot of bonds, and that takes a lot of mechanistic steps. All right, the next learning objective is going to be a little bit easier. It is a 4P, but it's a very, very short mechanism, and it's actually a mechanism that should look very, very familiar to you. All right, so this is learning objective 20L. And as I said, it is a mechanism 1. So it's the 4 Ps of imine or triple underlining or, because we're going to have to figure out when we form an imine or a ketone from nitriles and organometallic reagents. And if you're following along, this is chapter 20.17. Okay, so on our previous mechanism, we saw that our nitrile is electrophilic. We also saw it was a pretty weak electrophile, but we know that organometallic reagents are quite strong nucleophiles, all right? So our learning objective says this is going to be from a nitrile. So let's draw out our nitrile. This is going to be our weak electrophile in this reaction. And then we're going to have our organometallics. So this would be something like our organolithium reagent or organomagnesium reagent. Sometimes you hear these called Grignard reagents, but we can call them organomagnesium reagents so we understand them a little bit better. And this is going to be a strong nucleophile. Okay, so you can use whatever organometallic reagent you want in this reaction. All right. So the first product that we get in this reaction is going to be, I'll draw the arrows for this, an anionic species with either our lithium plus counterion or our magnesium bromide counterion, depending if we use an organolithium or organomagnesium reagent. And we're going to add our R group, our R1 group. All right, so we know the arrows from this. We know that our nucleophile, the bond, is what's going to be the source of electrons. Or if we were to draw that as a carbanion, we could start the arrow from there as well. So we're going to take our electron density. We're going to go ahead and have that electron density attack our carbon of our nitrile and break a CN bond. Right, and yeah. Oh, yeah, go ahead.
On the last reaction, last slide, did we compare the potassium throughout the whole
mechanism? Yeah, so if we were to draw that in, what the potassium would be, it would reform our KOH here. So yeah, thanks for that question. That's a great question. So we would end up with our KOH as our byproduct, and that would help us throughout the rest of the mechanism. So yeah, thanks for that addition. I appreciate that. All right, so we've got to this intermediate here, and we know that in our organometallic reagents, we need our H3O plus workup, and we would get an imine out of this reaction. All right, so I underlined in the learning objective, we can get an imine or a ketone. If we wanted to get a ketone in this reaction, all we would have to do is add heat in with our workup. And then we would hydrolyze that, and we would end up with our ketone as our product. Right, so it's a pretty cool reaction. You just need to change your workup conditions. And if you add some energy to this reaction, then we can go ahead and get to our ketone product, right? So you can form two separate products with the same set of conditions. You just need to change your workup in this reaction, all right? So we've talked about imine formation and that we can turn those into ketones. So we're going to do an addition reaction and an elimination reaction to get our oxygen there. All right, so it's really important that we can get two different products out of this reaction. So let's go ahead and take a look at our chime-in question for today. So let's see what we think about this synthesis. So this is a multi-step synthesis that we can have. And what do you think the product of this reaction is going to be? All right, you're always welcome to check with the person near you if you want to check your answer. I'll help you with a little hint, right? We talked about, making different groups if you need to add a carbon or not. Remember, your potassium cyanide does add a carbon in this reaction, all right? So that will give you that hint for what that intermediate is. The other hint I'll give you is looking at our workup conditions, right? We can get a couple different products depending on how we worked this up. All right, looks like about 50 people or so have answered. So let's go ahead and see what we are thinking here. All right, so we have a little bit of a split here for what we think is correct. So I see that a lot of people didn't answer A, which is great because that doesn't add a carbon for us. So that leaves B, C, and D, some pretty good choices here. So we certainly have seen Grignard reactions make alcohols. We've seen this a number of different times. So I can understand why people are thinking B. I think C and D are good answer choices, and I see most of you have chosen C because you didn't see heat in those workup conditions, all right? So we didn't go all the way to our ketone because we don't have heat. So I'll close the question here. All right, so for our chime in, the point was that our no heat in our workup. So that means we get the imine out. Right. And we added that carbon from that cyanide, which we've talked a little bit about. All right, so now we are on to our final learning objective. It's some more organometallic reagents, but instead of adding to a nitrile, we're going to add to a different carboxylic acid derivative. All right, and this is where we'll finish up. So our learning objective is 20M, right? And this is another one where we're going to need to know the mechanism. This is a 4P reaction, but it's going to be a mechanism that's pretty familiar to us. So it's a 4 Ps of formation of alcohols, right? So that's going to be our product. And this is going to be from esters. So that's our carboxylic acid derivative that we're focusing on right now. And organometallics. Right, so we've discussed in this class before that hydride reagents, H- reagents, are going to be pretty similar in reactivity to organometallics, right? The hydride is bound to a metal or a metalloid, putting that negative charge on the H. So it's not a proton, it's a hydride. So it turns out we can make alcohols from esters, from organometallics, or we could use hydride reagents to make a different product, but it would still be an alcohol. And if you're looking, following along in your book, this is 20.11. All right, so what we saw here before is we saw a pretty weak electrophile in our nitrile. We're going to see a pretty weak electrophile with our ester as well. So we can start out with an ester as our starting material, and this is our electrophile in the reaction. We're going to have excess organolithium or organogrignard reagent, or sorry, organomagnesium reagent. All right, or we said we can use our hydride reagents. So this would be, for example, lithium aluminum hydride. We've seen that be a pretty strong hydride reagent. We saw that was the only thing that would turn our, reduce down our carboxylic acid. All right, so these are all going to sort of behave the same way. They're all of these are a nucleophile in the reaction. And what we're going to get out in our first step so either R2 or H if it's the hydride reagent. We're going to get this as our intermediate. All right, so what happens when you have a ketone in the same flask as a organometallic reagent or hydride? Right, we know ketones react really well with organometallic reagents. So it turns out that we keep going in this reaction, and this is how we get our alcohol. So at first we have our alkoxide. We haven't worked it up yet. We're going to have R2 or hydride add in again. All right, and then we know for our organometallics and for our lithium aluminum hydride, we need to either have an acid or an aqueous workup. Then we can get to our neutral compound. That's in a separate step, right? Can't have those conditions in with our organometallic because it would react with that. All right, so the reason why I'm drawing these sort of in one with our hydride reagents is that we know that these hydride reagents react very similarly to our organometallics. Okay, I want to make a note about this intermediate is that the ketone is more reactive than the ester. So no matter what you do, you cannot stop at the ketone in this reaction. It will keep going. All right, and the mechanism is just very, very simple. We already know organometallics and how they react with this intermediate. So we'll take a look at the mechanism before that, all right? So on the exam, people always say, even if there's not excess listed there, it's always just gonna keep going. All right, so let's start out with our electrophile, our ester. We could say, for example, let's have a methyl ester that we have here, and we could have our lithium reagent, like a phenyllithium, for example. Right, we know this is a good nucleophile. We'll take that arrow from the electron density between the carbon and the lithium, but we know that it belongs to the carbon. We're going to attract that CO, break that CO double bond. This is exactly what you've seen before for organometallic reagents reacting with ketones. We now have made a new carbon-carbon bond. And we have our oxygen that is now anionic with our lithium salt as our counterion. Then we can go ahead and take the lone pair of electrons and assist the leaving of that methoxide. This is under highly basic conditions, so that's why we can have that leave. We don't need to protonate it first because we can't have protons in this reaction. Your byproduct in this case would be lithium methoxide. Right, and then you know this mechanism. Right, you know that we can add those Grignard reagents or those organolithium reagents to our ketone to be able to get down to our product. Right, hydride reagents act the exact same, right? Hydrides, that anionic of the H minus, so H minus reagents have the same mechanism. All right, that's all that I have for you today.